Now we move on to the uniqueness of Haar measure. And here is the statement. If mu and nu are left Haar measures, on a locally compact topological group G, then there exists a constant c greater than 0 such that mu is equal to the c multiple of nu. And now let's prove it. The idea of the proof is the following. Instead of working with the measures directly, we'll try to prove that the ratio, the integration of f against mu over the integration of f against nu is independent of the choice of f in CC plus G. And once this is proved, we can use the same argument as in the end of the proof of the existence of Haar measures to show that mu of u is equal to c times nu of u for any open subset u of G. Remember, back then we used Urson's lemma together with the monotone convergence theorem. We constructed a sequence of functions with compact support in an increasing manner, and they will approximate the indicator function on U. That was the idea. If you don't remember, just go back to my previous videos and you will see it. So here's the approximation of the indicator function on U from inside. I believe this is also a common trick in real analysis. Now, if we prove this, then since mu and nu are Haar measures, and thus radon. In particular, they have the autoregularity on the Borel subsets of G. We conclude that mu of E is equal to C multiple of nu of E for any E in the Borel sigma algebra of G. Again, this was in the proof of the existence, at the end of the proof of the existence. So the truly non-trivial part is to prove that this quotient, this ratio, is independent of the choice of f. Namely, it is a constant. This is not the end of the idea of the proof yet. We spent lots of time talking about just the idea. So let's continue with the idea of the proof, of the uniqueness. So usually, if you want to prove that this is a constant independent of the choice of f, then you want to prove the following. So normally, one might want to prove that for any f and g in cc plus of g, you have the quotient with f is equal to the quotient of g. However, our trick here is to fix a special h in cc plus of g, and prove that any such ratio with f is equal to this ratio with h. Or you can write this into a product by making the cross multiplication. This equation is so important, we give it a name, we give the star. So when we make this transition, although we do not have to pick two arbitrary functions, now we will face the difficulty of picking this special h. We're going to pick this h so well so that it will facilitate our proof. And now the question is how to pick this special h. And an intuitive idea is to use the symmetry of the group G. Of course, in some steps of the proof, we have to use the fact that G is a group. We have to use the symmetry in it. So the group structure is important here. We have to take advantage of it. But how? Here's the idea. Fix some h naught in cc plus of g, and let h of x be defined to be h naught of x plus h naught of x inverse. Clearly, h is again in cc plus of g. This is essentially due to the fact that the inverse map sending x to x inverse in G is a homeomorphism for topological group. And here you should observe that the support of this function, h naught x inverse, is equal to the inverse of the set of supports of h naught. So h is in cc plus of g, and h of x is equal to hx inverse. This is a good beginning for h. Maybe we want to have some more assumptions, restrictions on h. But let's see how far we can move towards this star equation just from this h, this simple h. And later, we may adjust this h in order to fit in some more general settings. But we do not know at this point yet. We will see.